Hello.
Hi. Are we live?
Let's have a check.
Yes, we're now live.
Oh, great.
Cool. Hello, everyone. Welcome to another UCCPS talk, this time by Andrej Ivašković. He's a Cambridge ICPC coach, and he's going to talk to us today about randomness and competitive programming.
Thank you very much for that introduction. Hello, everyone. As I've just been introduced, I am indeed the Cambridge ICPC coach, and I'm also a PhD student at the Computer Lab, and I work in the design and semantics of programming languages. Now, in this talk, I will talk about randomized algorithms, and in particular, how to utilize randomness when you want to solve a problem in a programming contest. If you're watching this as a live stream, then feel free to ask questions in the YouTube chat, and one of the wonderful UCCPS people will relay it to me. So I will briefly start by saying what randomized algorithms bring to the table, and it turns out they have some very interesting advantages. I will introduce some simple terms and review some concepts from probability. Now, I assume that most of you are acquainted with some of the probability basics, but I'll quickly go over the terminology that I'll use in the talk. Next, I will go over a few toy examples, and the first one will be just searching an unsorted array and attempting to find a value in sublinear time. Well, it's not possible really to do it in sublinear time, but we'll see how well we can do. This will show us how to estimate the probability of the algorithm succeeding. Next, I will look at an actual ICPC problem, which is a computational geometry problem. Computational geometry questions can honestly be quite annoying to deal with, but this one is rather simple, and I find the solution very elegant, and I think you'll like it too. Finally, I'll focus on a more involved algorithm with a hardware analysis, that being Karger's algorithm for computing the minimum cut in a graph. So, why randomness? It might seem odd to talk about randomness in the context of competitive programming, where the focus is on coming up with algorithms that pass some number of test cases. But this very format of programming contests is exactly why randomness is useful. You only have a finite number of test cases, and all that matters is that your solution is evaluated and returns a correct answer while satisfying some time constraints. So given that it's evaluated in a finite number of cases, all that matters is you have to pass this number of cases. So it might be the case that solving a problem exactly for all inputs is computationally expensive if you use the algorithms you come up with. They might use up too much space, or they have a high running time. So this is, in general, a natural setting for using probabilistic or statistical methods. And I'll show this in a real-life example. Are there more mathematics or computer science students attending this talk? Now, what I can do is choose a few people currently watching this on YouTube, just ask, and just make an estimate or prediction based on this. Now, it would be much quicker to, this is much quicker than me asking everyone, like, what course are you doing? Or setting up a poll, or having to go through answers in the chat or anything like that. So just taking a small sample and saying, okay, I'm going to rely on what the majority says in this case is going to be a quick and dirty solution that, if I pick people uniformly at random, is going to give me a pretty good idea about what the answer is. You might be solving a problem and you come up with an algorithm that is just great and always returns the right answer and works very well in practice, but there's a very predictable, very small set of test cases on which the performance is really bad. Maybe you come up with several variants of the same algorithm that each encounter a different small set of pathological test cases. So someone who is a test case writer and is particularly malicious and wants to break your answer, so they might be aware of what solutions you might attempt, and the test cases might be those edge cases that end up failing your solution entirely. And this is something that actually comes up quite a lot, and you've probably already seen this. Quicksort has a very good running time and sorts the array quickly in very many cases. But for arrays that are sorted or almost sorted, it has the worst case quadratic running time. The simplest solution to this issue is to just shuffle the array you're given initially, so the attempts of a malicious test case writer to fail the solution are completely foiled. Now, this doesn't reduce the probability of hitting the pathological case, but it does make it harder for the malicious test case writer to present the input in this particular way. So let me just immediately get something out of the way. This is not a talk about approximation algorithms. That's a completely different paradigm. There might be an interesting talk about approximation algorithms and all the terms that come with it, like fully polynomial time approximation schemes and so on. But they don't tend to be used in competitive programming much, other than in something like CodeJam, or where you're trying to find an approximate solution. Sorry, not CodeJam, in Google Hashcode, we're looking for an approximate solution rather than something that's supposed to pass test cases as well as possible. So this is an interesting topic in its own right, and I highly encourage all computer scientists, whether they're interested in competitive programming or not, to take a course, if available, on approximation algorithms. If you're a student at Cambridge, the course in question is Advanced Algorithms, which is lectured by Thomas Zerwald, and I highly recommend you take it. The goal of randomized algorithms is then not to give like approximate answers or anything like that. The goal is to output correct answers with some probability. You also want to be certain that the randomized algorithm is going to have a chance of passing every valid test case. So for any particular input, the probability that you return a correct answer is supposed to be something that's not zero. So you need a non-zero probability of passing every single test case. By contrast, approximation algorithms are not concerned with producing a correct or optimal solution in every single test case, but they want to have a guarantee that the return solution is close to the expected one within some degree of precision or tolerance. They do have some interesting similarities, though. So randomized algorithms might have their running time affect the probability of returning the correct answer. And so do the approximation algorithms, actually. So in the case of randomized algorithms, and going back to the example I gave earlier, if I asked 7 random people in the audience what they studied, then I would have a higher probability of getting the correct conclusion than if I asked only 1. So this is one similarity. Another similarity is, well, in this case, a contrast that they have is that randomized algorithm can be used pretty much across the board in almost any setting, whereas approximation algorithm will almost always be used in optimization problems. Now, you can use approximation algorithms and the associated theory for many other problems, but the language we use to talk about the properties of approximation algorithms is almost always, almost exclusively that of optimizing something that we'd usually refer to as an objective function. So you might need to rephrase your decision problems as optimization problems if you're dealing with approximation algorithms. So the knapsack problem is a classic example where approximation techniques are used, and you want to fit items with as high of a total value as possible. On the other hand, for those of you acquainted with Boolean satisfiability, that's a decision problem, where the answer is either yes or no. You can indeed interpret it as an optimization problem by just asking, what is the greatest number of simultaneously true clauses under some assignment to variables? But now this has become an optimization problem. It's no longer decision. It's not yes or no. It's what percentage of them or what proportion of clauses are satisfied. It is also possible for an algorithm to be both an approximation algorithm and utilize a random number generator in it. So yes, randomized approximation algorithms are a thing, and Boolean satisfiability has a pretty good and pretty simple solution using one such algorithm. We tend to talk about two broad classes of randomized algorithms: Las Vegas algorithms and Monte Carlo algorithms. Las Vegas algorithms are those that guarantee that the returned answer is correct, but their running time depends on what the input is, and it could be infinite. Their expected running time, the mean running time, is something that should be finite, and it should show a clear advantage of a deterministic algorithm. So on average, it gives you a better time than a deterministic algorithm, but in worst case, it could indeed run infinitely long. Monte Carlo algorithms, on the other hand, have a predictable running time, but they have a non-zero probability of returning an incorrect answer. In this talk, our focus is on Monte Carlo algorithms. Okay, so let's have a brief review of the main concepts in probability that we'll use in this talk. And we won't do it in a formal way. It's just going to be a quick review of what these concepts are. The key concept is that of an event, and it can be seen as a set of outcomes of some experiment. These events are assigned probabilities, and a probability is just a number between 0 and 1 inclusive. For our purposes, we have kind of a frequentist view. So a probability of an event corresponds to how frequently it is expected to occur on repeated experiments, or if you will, a proportion of the desired outcomes compared to the total number of outcomes. So, for example, the probability of getting head when you flip a fair coin is 1/2. So it's one outcome out of 2 total outcomes. So we use this P of E notation to refer to the probability of an event E. Since an event is seen as just a set, there is an empty event, which necessarily has probability 0, and there's the certain event omega, which has the probability 1. This certain event omega is really just the set of all of the possible outcomes, and all of the events are subsets of this set omega. And because these are sets, it makes sense to look at intersections and unions and complements, all set operations. So we refer to these intersection events as joint events, and we use this comma notation. Unions are just, well, written as unions like here. And the complement event is really just the event that says, oh, E didn't happen. What are all the other possibilities? So it's the event that's disjoint from E, and when you take the union of them, that gives you the certain event. There is a very useful rule for estimating probabilities of some events, and it's called the inclusion-exclusion rule. This rule is very similar to the rule with the exact same name in set theory. And yeah, you can see that if you got rid of the probabilities in here and you inserted some unions and some differences, you will see that this is exactly the same thing. So the probability of a union of 2 events is equal to the sum of the probabilities of the 2 individual events minus the probability of the joined event. And this is something that can be generalized further to some n events rather than just 2. If you just look at E1 as some event E and E2 as its complement, the consequence of this is just that the probability of E plus the probability of its complement necessarily add up to 1. So this is a useful rule sometimes, and we will be utilizing it in one of the examples in this talk. Now we turn to the concept of conditional probability, which we don't utilize too much in this talk other than implicitly near the end. However, it does introduce a concept of independent events, which is something that well, refers to all of the independent runs you'll be doing of the randomized algorithm. So it's a very important, actually, concept. So we define the concept of conditional probability. And conditional probability, written like this, a probability of E1 given E2, is something that is defined as this quotient here, P of the joint event of E1 and E2 divided by the probability of E2. In other words, if you know that E2 happened, what is the probability of E1? Well, it's just the probability of E1 and E2 both happening, but then you have to scale it according to the probability of E2 happening. Now, what if we know that whether E2 happened doesn't affect the probability of E1 happening and vice versa? Well, that means that E1 and E2 are independent. And this is expressed with these equations here. So essentially, we say that two events are independent when one of them occurring gives you absolutely no information about the other one occurring, whether it's more or less likely. Now, there is an equivalent and frequently more useful definition and interpretation of independence, and it's this one. The probability of the joint event is equal to the product of the probabilities of the events E1 and E2. And this is a very useful fact. You'll hear it referred to as a product rule sometimes. Now, the first example of how this rule comes out in practice is when you're trying to come up with a randomized algorithm and you need to figure out what probability of success do you need in order to be confident that your solution will actually pass the grader. Because it's not really that you evaluate your solution in a single test case, there'll be multiple test cases. So let's say that the desired success probability for the whole batch of n test cases is P. Now let's introduce the event where you pass the ith test case Ti and assume all of the runs, all of the test cases are independent. So then this probability P has to be less than or equal to the probability of the joint event of all of them passing. Now, if all of the test cases are independent and all of the runs are independent, then we'll just estimate it using the product rule. And we hand wave and say that the probability of passing every single one is the same, or you can take maybe the least one of these probabilities if you want, and we just get this a probability of some ith test case passing to the power of n. So actually, the probability of you passing an individual test case should be at least the nth root of P. So if you want to have a probability of 0.75 that you'll pass all of the test cases, and you know that there are 20 test cases, you plug these numbers into a calculator and you get that actually the desired success probability is roughly 0.986. So when you're dealing with a randomized algorithm that has like an 80% chance of success, if you then have to deal with even just 5 test cases, the probability of all of them passing is now not that great, actually. Now let's actually turn to the first problem, our first example, and this is something announced earlier. Let's say you're given an array A that has length n, and you're asked to find a value that appears at least p% of the time, or you have to determine that no such value exists. The constraint is that p is between 40 and 80. So you're not looking for the item that p is the greatest number of times. You're not looking for a particular value that you've been given. You just ask, is there a number that occurs between 40 and 80% of the time, or p% of the time at least? Now, you could do this easily deterministically using a sorting solution. You use a quick sort or merge sort or whatever sorting algorithm of your choice is, and see what is the longest consecutive run of equal items in the array, and you compare this with n times p divided by 100. Now, this is dominated by the sorting, and if your sorting procedure is n log n, that's not so good. Now, you can think of an alternative solution that you will hear claims that this runs in linear time, and for the most part it does. So this is a solution based on hashing. You create a map from array items, from the values you see, to the number of their occurrences. So you have to scan the array and you fill in this hash table. So then you scan this map and you see if any of the keys map to a value that is at least n times p over 1,000, over 100. And if there is, then you return yes, otherwise no. And this is guaranteed to work. Now, what you have is that the expected running time of this is O of n, though you might have large constants. And remember that this is hashing, and hashing can have some actually really bad worst case performance if you're very unlucky with hash collisions. So hashing is something that you usually claim gives you constant time updates and accesses and so on. But actually, that's just the average case. You might get pathological cases. So this is kind of similar to that quicksort problem we've addressed earlier. Now let's look at an actual probabilistic solution. So you might have this value that occurs many, many times in the array. So if you just choose an item at random, there is kind of a significant probability, a pretty good chance that you'll be randomly picking it out of the many values that exist in the array. So if the value occurs with probability 0.6, then there's a 0.6 chance that that is the value that you picked out. So here's the idea. You pick an item, you scan the array, see how many times this value occurs in the array. If it occurs at least p% of the time, you return this value. Otherwise, you run again and you try the experiment. Maybe you just got unlucky the first time round. And you run it k times. So you chose k array items, and you're hoping that in one of these k attempts, you got lucky and you managed to find this frequently occurring value in the array. So if you fail in all of these cases and you didn't find this value, you're going to return failure and say, oh, no such value exists. Otherwise, you would have returned previously and you would have reported a frequently occurring value. So the only way you could have answered incorrectly is if such a number does exist, but you got so unlucky that you never picked it in any one of the k iterations. Otherwise, you're guaranteed to be correct. So let's look at this solution in an actual example. So suppose we have this array 3, 2, 1, 5, 2, 2, 1, 2, 2, 3, 2, 7. And suppose that p is 45. So we're looking for a value that occurs at least 45% of the time. Now, if you do the count and you see that this 2 that occurs many, many times, it actually occurs 5 times out of 11, which is more than 45% of the time. So we ideally want our algorithm to return 2. And let's look at a run. We choose the value 1 and see that 1 occurs only twice in this array. The answer is no. We choose 5, and it occurs only once. So the answer is no. And then third time's the charm. We choose 2. We see it occurs 5 times. That's at least 45%. Therefore, we return 2. Now, as you see, we were unlucky in the first attempt, unlucky in the second attempt, and then finally in the third attempt, we got lucky and we found it. Now, the question is, how many times should we repeat the experiment to have a good deal of certainty that we're not really getting very, very unlucky. We want to be as certain as possible that our answer is correct. So what value of k should we choose? So we'll do a quick and simple analysis, and we'll assume the worst possible conditions, and we'll assuming that this is a test case on which this value exists, so it's possible to fail. So a test case only fails if each of the k independent attempts selects one of the 100 minus p% of the values that do not occur at least p% of the time. So in the worst case, this is when p is 40. So with this proportion 40, you're most likely to get unlucky in any individual run. Suppose now that we computed that the success probability in each test case should be at least 0.995. And I believe I came up with this number by saying that there are 100 test cases and you want something like 0.9 probability of passing all of them. So what we're looking at is we want the probability of passing all the test cases to be at least 0.995. And this probability is just 1 minus the probability of failure. And you fail in each of the individual test cases with this probability, 1 minus p over 100. And because you repeated k times, and these are k independent runs, you raise it to the power of k. And as I said, the worst case is when p is 40. So it's really just 1 minus 0.6 to the power of k. If we try to solve this inequality right now, k has to be greater than or equal to 0.9995. You take the logarithm of it. Okay, you have to put everything on one side of the equation. So you get that 0.6 to the power of k has to be less than or equal to 0.005. Now you have to take the logs of both sides. And what you get is that k equals 15 is already very good as a solution. So all you have to do is run this procedure of randomly selecting a value from the array, seeing how many times it occurs. And already with k equals 15, you get this very, very good probability of passing all the test cases. Now, I presented these two solutions, one based on hashing and the other one based on just random selection. And let's actually see how this works in practice. Well, I'm not going to show you the code, but I put a link to a GitHub repository where I've implemented these two solutions in C++. And I'm using just 3 randomly generated test cases, each with 1 million array items. The hashing solution ran in almost 3 seconds, whereas the randomized solution ran in half a second when you add up all of these 3 test cases. So it is like a pretty significant factor. And of course, if you use the solution based on sorting, you wouldn't pass at all. So do we have any questions in the live chat right now? Like, have we had any questions so far?
No, I don't think there have been any questions as yet.
Cheers. Right, let's move on to the next question then. So the next question was actually at the Northwestern Europe Regional Contest in 2014, which was actually when I went to this regional contest when I was in my first year of my undergraduate degree. And it was problem F, finding lines. So the question is, you're given a set of endpoints where n is up to 10 to the 5th, that is 100,000, and you're given a proportion p, which is between 20 and 100. This is really a percentage, really. So you're asked whether it is possible or impossible to draw a line that goes through p% of the points. Now, I've drawn this example where I don't really state what n or p are, but you can see that there is a line that passes through 4 of these points, and there are some lines that pass through 3 points. but this is the only line that passes through 4 points, and there's nothing that passes through 5 points. So for different choices of p, you'll have different answers. Now the question gives you a 4-second time limit. And when you look at these constraints, you first think about all of the solutions you can think of immediately. And the naive solution is something that just says, okay, let's look at every pair of points in the set, and these 2 points are going to define a line uniquely. We're assuming that no 2 points are identical, of course. So you pick 2 points, they define uniquely a line, and then you check how many of the other points are on this line. So if you do it for all pairs of points, that requires all of n squared choices of these pairs of points. And then you have another O of n check to see how many of these points are on this line. That's cubic time with n up to 10 to the 5th. That's not going to work. So this solution is not feasible. We want to get something that works in a much better than cubic time. Quadratic time is not going to pass. N log n time is pushing it. So linear time seems like a plausible option, but how do you even do something like this? Well, the answer is you need to come up with a randomized algorithm. So let's use a similar idea as previously. Rather than trying to go through all pairs of points, let's just choose one pair of points. So pick some 2 points from the input set and check whether the line passing through them also passes through at least p% of the points. Aha. So we are not checking all of them. We're checking just one pair of the points, and we're hoping that we're getting lucky. And if we did get lucky, we just say, we found it, it's possible. Otherwise, we repeat this, and we repeat this up to k times. So yes, if at least one of the k lines that you chose had p% of all the points on it, you return possible. Otherwise, you return impossible. And once again, the answer can only be incorrect if such a line exists. But we're unlucky in each of the k attempts. So the running time of this algorithm is very simple. It's just O of n times k. So this k affects the running time. And obviously, if you've chosen just a fixed pair of points that define a line, then going through all of the points is just O of n. So if n is up to 10 to the 5th, then we can easily get away with k equals 500. But let's see how well this works. So the probability of choosing a line that passes through the desired number of points is roughly p divided by 100 squared. So if p is 40, for example, sorry, when p is 20, you plug this in and you get a probability of 0.04. That is very low. But once again, don't think about the probability of success in an individual run. Think about the probability of failure in an individual run. The probability of failure is 0.96. And if you repeat it an adequate number of times, you're going to get actually a very low probability of all of the runs failing. So this is what you get. The probability that the answer is correct when k is 500 is equal to this, 1 minus 0.96 to the power of 500. Aha, so this is something quite good. And I could just spit out a number, but just to show that this is like really, really good, let's further assume there are 100 test cases. So now the probability of passing all of them is equal to what the previous probability of passing individual test case was, to the power of 100. assuming that all of the test cases have this possible failure mode, that the line does exist, but we got unlucky in every single case. And if we evaluate this, we get something that's probably going to pass. It's pretty certain. So I want you to appreciate this. We're given a question in computational geometry, yuck already, that the first solution we come up with is something that's cubic time. And then we just take the same solution, get rid of the outer loop that goes over all pairs of points, and just say, oh, let's sample from some pairs of points. And immediately you get something that's essentially linear time, obviously times the number of runs, that works pretty good. So appreciate the simplicity of this, how few steps you actually need compared to the trivial first algorithm you come up with to get something that passes definitely on any grader. And in fact, this is the official solution. This was the official solution at the contest. And I am not sure that anything quite like this exists with these constraints that it is deterministic. So let's think of the takeaways thus far. There are some similarities between the solutions of the previous two problems. In essence, it's about doing a simple procedure many, many times and seeing if any of the runs produced a solution or found something. So this can give us a surprisingly good result, as we've just seen. So it was just pick a value from an array and hope you get lucky. If you got unlucky, not a problem. Just repeat it several times. And 15 was already quite good. With finding lines, it was choosing a random line out of obviously those valid lines that you would consider. So you take a pair of points rather than an arbitrary line in the plane. In both of these settings, the error was a constant. So 0.04 was a probability of success, and the error was 0.96. So even though 0.04 is small, this is still better than 1 over n as n grows and grows and grows. So the number of runs was not affected by the size of the input. So we always had a pretty good idea what we needed to do. So in a way, we were lucky thus far. And it's not clear whether we can do anything if the probability depends on the size of the input. But now we'll turn to a problem where the probability of failure and the probability of success do indeed depend on the size of the input, but we can do something about it. Do we have any questions in the chat?
No, I think the explanations must be very clear since there's no questions.
Great. Right. Let's turn to the last problem we consider, and that is the minimum cut problem. This is actually edge connectivity, but I'll refer to it as minimum cut because this is what it really is. So given an unweighted undirected graph, we want to split its vertices into two non-empty sets, such as the number of edges that connect vertices of different colors or belonging to the two different sets is minimized. We refer to these edges as the ones that cross the cut. So consider this graph here. I've split it into two sets, one blue and one red. So these two are blue, these three are red, and the cut value is 5. So you count the edges. There's this edge here that crosses the cut. There's this edge here that crosses the cut. And there's these two that cross the cut. There's this one that crosses the cut. So 5 edges cross the cut. Now, if we want to actually minimize this, we can do so much better. We choose just one of these vertices, and we choose the one that has the least degree. And in this case, the cut value is 2. Now, it's not always the case that you're going to pick just one vertex that has the least degree, but that gives you kind of like an upper bound on, it gives you a bound on how low the minimum cut can go. So it can definitely go lower than that. And here's an example where the minimum cut is not taking just one vertex in one of the sets and all the other ones in the other set. So you have these two triangles. There's an edge connecting them here. So you just color these two triangles with these two different colors. And here the cut value is 1. Now, minimum cut is a very well understood problem, and it's mostly actually phrased in the context of flow networks and directed graphs and edge weights and so on. And there are some really well-known results from work on flow networks, and in particular, it's the max flow min cut theorem. What the max flow min cut theorem says is that when we're looking at this problem in this directed weighted setting, we define the cut in a slightly different way, but it's really just equivalent to finding the minimum of all maximum flows so it's equivalent to finding the maximum flow between the source and the sink. And then once you've constructed all of these flow networks, you take the minimum of all the maximum flows. So if you just look at one flow network, you look at those edges that are filled completely, like in terms of capacity, and that tells you what the minimum cut is going to be in this case. So in this case, it's S is in one set, and all of the other vertices are another one. And you can come up with a few equivalent min cuts as well, but this is the one we'll choose. So if we look at the possible solutions, so if you want to have this flow-based approach deterministically, what you can do is you can choose every pair of vertices in the graph and run a max flow algorithm for these vertices for this source sink pair. So the running time is n squared, number of vertices squared, times whatever the running time of the flow algorithm is. Now you can be clever and you can just say, oh, actually, we know that if we select an arbitrary vertex in the graph and just look at what the sink is among all of the other vertices, we know that at least one of these is going to return a valid cut. That's fine. So we fix the source ahead of time. We don't loop over it. We just loop over the sink. So we get it down to n times the running time of computing max flow. And there are several efficient max flow algorithms. There are obviously the inefficient ones like Ford-Fulkerson, Edmonds Cup, those that they teach in undergraduate courses on algorithms. But competitive programmers will be more acquainted with Dinnick's max flow algorithm and FIFO push relabel algorithm. They can be a bit of a pain to implement though, unless you have it already in a library or you memorize it or written it out 50 times, you might have a few issues when you're trying to debug these algorithms. So flow in general is a little bit painful if you're forced to use some of these very efficient algorithms. So let's turn to a randomized approach. And this is so-called Karger's algorithm. This was developed in the 90s, in 1993. And it goes as follows. You choose a pair of neighboring vertices and you say, okay, these vertices belong to the same set. They're in the same side of the cut. They have the same color. And the way you choose them is you choose them by selecting the edge uniformly at random. So there's edges in your graph. You choose an edge uniformly at random, and then you merge these two vertices into a single vertex. So now from a graph that had n vertices, you have a graph that has n-1 vertices. The edges that connected these vertices are now gone, but you had to reroute some of the other edges that touched these two vertices that now got merged. So the remaining edges, so when you keep repeating this, you go from n vertices to n minus 1. You repeat it from n minus 1 to n minus 2 until only 2 vertices are left. Now, this isn't just a normal graph, it's a multi-graph, so you might have multiple edges between 2 vertices. And the remaining edges represent the cut. The number of edges you have is the value or the capacity of the cut. And what you do then is you run the procedure many, many times, and you report to the answer that has the least number of edges. So this is the contraction procedure, where it takes a graph G with vertices V and E, while the number of vertices is greater than 2, you choose an edge E from the set of vertices uniformly at random, and you update the graph so that you remove the edge E and you perform like this contraction, and then you return the only cut in G. Picture, say, 1,000 words. So what contraction means in this case is you might have this graph A, B, C, D. You want to contract this edge connecting A and B, and you end up with a graph where A and B merge into a single node called AB. And notice this thing. C had an edge to A, so now C has an edge to AB. But both A and B had edges to D, so now you have 2 edges between D and AB. So keep this in mind. Obviously, if there were other edges between A and B before this merging, they would disappear. You're not going to have self-edges. And now let's see how the algorithm works in an example run. So consider this 6-vertex graph with nodes A, B, C, X, Y, Z. And it's kind of similar to the 2 triangles example we had previously, except now there are more edges. So suppose in the first step, we choose the edge between A and C, and we want to contract it. So now A and C are merged into a vertex that we call P. Now both A and C were connected with B, so there are 2 edges between B and P. Now we decide to say merge X and Y, and they get merged into a node Q. Now we merge, say, this is a type of P and Z should be merged. So, Q and Z are merged and they produce a node R. And this is the graph we get. So we merged 2 vertices that had 2 edges. So the other one disappears, but we now still have edges between P and R. And let's say we merge B and P. And we just get this graph with 2 vertices with 3 edges connecting them. In this particular run, we got lucky because this indeed does correspond to the minimum cut. You can kind of see exactly how each one of these 3 edges has, let's say, evolved over the course of this algorithm, and which edge in the original problem it corresponds to. Similarly, you can see how all of the edges, all of the vertices at the very beginning correspond either to S or to R. So they really represent the 2 sets or the 2 colors. Now let's analyze this algorithm. So what is the probability that the contracted graph exactly corresponds to a minimum cut? Well, this is going to be very difficult to say because the minimum cut is not necessarily unique. It is also going to be very difficult to reason about a whole lot of things. So we're going to assume the worst possible case where the minimum cut is unique, and we're just going to say, let K be the number of edges that it has. So we're interested in choosing only those edges that do not touch any of the k edges in the minimum cut. So we never contract one of these edges. So in a single step, the probability of choosing an edge that is not in the minimum cut, if we have m edges in n vertices, is given by k over m. That makes sense. It's just one step, right? So in one step, we the probability of choosing an edge that is in the minimum cut is k over m. Now, m is the number of edges, and we can use a fact from graphs that is very well known, which is that 2 times the number of edges is equal to the sum of the degrees of every nodes, degree being the number of neighbors. Now, the degree of every single one of these nodes is, well, it is at most k. And the reason for that is that if you have a minimum cut with k edges at most, you know that you're going to have every single node have degree that is less than or equal to k, because obviously one of the possible cuts is choose a vertex that has the least degree. So this is the inequality we get. We get 2k over 2k divided by nk. So the probability is 2 over n. And this is just in one step. So to bound the probability, Pn, that a graph with n vertices doesn't touch the minimum cut C, well, we used kind of like a little recurrence. And we're being also very pessimistic about these things. We say that the probability of not making a mistake with n vertices, well, it's just a matter of not making a mistake in with n minus 1 vertices times not making a mistake in this next step. So this is a recurrence relation, and you can see this is a product rule. We assume that all of these steps will be independent, that we're not making a mistake in any one of them, and we're leaving it alone. So if the probability of choosing an edge that wasn't the cut was 2 over n, then the probability of choosing an edge that's not in the cut is 1 minus 2 over n. And then in each of the successive turns, we choose an edge that is not in the minimum cut. And if we expand this out, we get this product. We get that Pn is greater than or equal to n minus 2 over n times n minus 3 over n minus 1, and so on. And you'll notice that this n minus 2 and n minus 2 cancel out. So it's kind of like a telescoping product. And if you write it out nicely, you'll get that Pn is greater than or equal to 2 over n multiplied by n minus 1. All the other terms cancel out. So the probability of success isn't too good. As you can see, it's kind of 1 over n squared. So it's not good. So we need to repeat it many, many times to actually have guarantees that this works. But how many times? So if the probability of success is around 2 divided by n times n minus 1, or if you will, 1 over choose n2, or n choose 2, the failure probability after k contractions is, well, you just take 1 minus the success probability to the power of k. Now, if you have something like 1 plus or minus something close to 0 to the power of something that is very big, usually the definition of E comes into play. So we use this fact about the definition of E. It's just the limit as x tends to infinity of 1 plus 1 over x to the power of x. But this has a plus in there, whereas we use a minus. So the thing we actually use is the fact that 1 over E is the exact same thing, but you put a minus sign instead of a plus sign. So if we let k be equal to n times n minus 1 over 2, the probability of failure is approximately 1 over e. So something like 0.4 or whatever it's supposed to be. Now, probability of failure being 0.4 isn't that great. Yes, so this isn't that great, but we can do better if we choose a greater exponent, a greater value of k, and we just go further with this fact and just say that 1 over t, that's 1 over e to the power of log t. So we just put an additional log of t in the exponent. So our choice of k is going to be what choice of k was here, n choose 2, times the logarithm of n. So if we choose this, the probability of failure turns out to be quite nice, actually. It's just 1 divided by the number of vertices. So if we run n choose 2 times, right? So if you run n choose 2 times the logarithm of n times, the probability of failure is 1 over n. So success probability is n minus 1 divided by n. And you do it in n squared m log n time. And this is the same as Dinich's algorithm. Now, I presented just a randomized solution that had an involved analysis, and it turns out it gives you a running time that is the same as something you already maybe know how to do. Maybe you'd struggle with maximum flow and debug it, but it's still like a deterministic algorithm does quite well. Well, there's an improved version of this algorithm that has n squared log cube n running time. So Karger-Stein's algorithm uses pretty much the same idea as Karger's algorithm of contraction, and it aims to resolve the major issue of Karger's algorithm, which is that the number of independent runs is too high. The first insight is that we can use an exact algorithm for small inputs, where the probability of doing something wrong is the highest. You can use something like a brute force solution if you have a graph of 5 vertices or less. Otherwise, you can contract a graph a bit, for example, until the number of vertices halves, and you do that twice, like 2 independent contractions. And then you recursively contract to these 2 graphs, and you compute the minimum cut for the 2 solutions. Now, if you actually want to get this running time that I'm advertising, you don't halve the number of vertices, you do something else, and the exact amount of contraction you have to do in each of the recursive steps can be derived from the probabilistic analysis. And if you solve all of this, you get this running time. And that's quite nice. Now, if you want to solve the weighted version of this problem deterministically, there are good algorithms for that. There's the Storer-Wagner algorithm, and it runs in O of n times m plus n squared log n time. But you need to use a Fibonacci heap for this, and you use that adjacency list representation. You probably won't be able to write out a Fibonacci heap during a contest. It's way too involved, and it doesn't exist in standard libraries. So if you want to have a better idea of what the running time is if you use matrices and not using heaps, it's n cubed. So n squared log cubed n versus n cubed, Karger-Stein's algorithm is slightly better. So there are a few things to keep in mind before I wrap up, just practical advice. In general, it's best to use srand time null if you're writing your answers in C++. Some contests do place limitations on the use of time, and they force you to use a fixed seat. Make sure you check out the contest rules about this. To the best of my knowledge, using randomness in an online judge is not restricted. You can use time and so on. You might just get some behavior that you're not necessarily expecting. In all of the problems that we looked at, we were sampling from a uniform distribution. All of the items in the array were equally likely to be chosen. All of the point pairs, the lines were selected with equal probabilities, and all of the edges in the contraction in Karger's algorithm were selected with equal probabilities. You can easily get this wrong, and sometimes the hardest part of the implementation is ensuring this uniformity. Now, this matters for the sake of avoiding some pathological cases, as your simple proof attempts will get broken. They have nothing to do with what your algorithm is actually doing. Of course, sometimes you don't want uniformity, or you can phrase the distribution that you're sampling from as explicitly a non-uniform one. Like, for example, in Karger's algorithm, rather than having 3 edges between vertices, you assign weights, and your sampling is based on these weights. When you have a guarantee that the sampling distribution is exactly what it should be, try doing that quick analysis, that quick proof, to see if you can estimate the probability of success. And it's usually simple. It's unlikely you'll have to do some tough estimates and have to use involved maths, but in some cases you do have to write out a recurrence relation or use some facts from analysis or number theory. Basic knowledge of combinatorics is usually sufficient. The best resource is always solving more problems. And I'll take this opportunity to invite you to participate in the UCCPS contests, including the one that I believe already started today. And you might even use some ideas from this talk. In addition, sign up for UK IPC. I'm looking forward to seeing more registrations, and I'm quite interested to see how all of you'll do. And I always encourage all of the people that I supervise for algorithms to sign up for UK IPC just as a general exercise. This is very useful, even if you're not that into competitive programming. The deadline for registration is the 9th of December. So 9th of December is the last day to register, and the date of the contest is the 12th of December. No doubt you've previously been told about the Competitive Programmer's Handbook, which is mostly a fine reference. So chapter 24 talks about probability and randomness, and it has a very short section, randomized algorithm. It's not exhaustive and it's not detailed. However, that chapter also covers Markov chains, and it also talks about things in probability such as random variables. If your only exposure to probability is doing very closed form problems where you're told about all of the random variables you need to look at and computing expectations in a sense that isn't really practical for problem solving, there's a very nice example there of how you can use random variables to solve some problems. And obviously there are problems related to probability and contests that have nothing to do with randomized algorithms or computing probabilities. So it is useful to have a look at this reference. This book, Randomized Algorithms, is an introductory text on randomized algorithms, but it's an introductory text for graduate level courses and for people who want to do PhDs on this topic. It's quite old now, and you don't really need to have much knowledge of more modern, newer randomized algorithms. So it's a lot harder than a lot of the other resources that you'll find online. So have a look at it if you're interested in the topic beyond competitive programming. And as always, there's Introduction to Algorithms, the famous CLRS book. And in even, I believe, the latest edition is chapter 5. Chapter 5 is more of an intro to probability and showing how you can use it for algorithm analysis, especially average case analysis, rather than designing randomized algorithms. Probability tends to be used to analyze running times of some data structures such as hash tables. So remember that most of the claims when it comes to hashing are averages, and in contests you usually rely on this average and hope that you're not going to hit the pathological case. And that's pretty much similar to us using randomness anyway. As you would see if you read this chapter of Introduction to Algorithms, language of probability is useful for all sorts of analyses, not just for randomized algorithms. Let's briefly summarize what I said in this talk. We looked at 3 search problems. We had 2 decision problems, and we had an optimization problem. And we resolved them all with simple randomized solutions. We didn't use much probability knowledge past the basics, and the most involved piece of maths was knowing things about the exponential function and playing around with estimations. If you're experienced, you would have seen it before, but if not, you can just play around with the calculator because you don't really care about what the O notation says. You might care more about the exact numbers. All of the solutions were based on iterating the same procedure some number of times, and then using the product rule for these independent runs. Even if you know an efficient deterministic solution, there is value in using a randomized solution because it could be quicker to write, it might have a very good probability of working, and you never know exactly how bad of a constant factor you might have in your deterministic solution. And I'll leave you with this thought. A complicated deterministic solution is less certain to work than a simple randomized solution with a good success probability. Thank you all for listening. A big thank you to UCCPS for hosting and organizing the talk.
Thanks so much, Andrej.
I'm happy to take any questions if there are any in the live YouTube chat.
I can't see him.
I think some people might be wondering how to register for UK ICPC and what to do if your team is not accepted immediately.
Aha, so okay, so for registering for UK ICPC, you need to go to the official UK ICPC website. There's going to be a link to registration on the global ICPC website. Just create your team. Register yourself as an individual because it is individual this year. Since I'm the one who approves all the teams that are competing, say in Cambridge as a location, you have to wait for me to approve it. And I have a look at it every couple of days, and I try to make sure that nobody waits for more than a couple of days. Also, ignore the predicted ineligible. That's there by default. And it's absolutely fine if you're listed as a student coach and the team seems empty.
Okay, it looks like we actually have some questions coming in on the chat now. So someone asks, what are some examples of typical competitive programming problems which are better solved with a randomized algorithm?
Right, so usually it's trying to test a particular property where if you wanted to do it in a way that is exhaustive is very difficult. So you might be interested in whether a certain number or a certain string satisfies some property, like we talked about, like the 40-60% properties. So something that you could, I guess it's very similar to any problems in NP in that it's very easy to verify certain things, but like making sure that it's exhaustively done or finding that initial thing verifying that the answer is yes, that's an example of such a problem. And indeed, the finding lines question was something that was at ICPC. Other problems you might encounter are things that require strategies that aren't even this involved, like we've done it before, but you can get a question where it's all a matter of literally doing complete guesswork and doing this guesswork 1,000 times. So if you have a question like, oh, is a graph bipartite or something like that, or satisfied some coloring conditions and it's a small graph and you can't be bothered to write a solution that actually does this properly and checking that there is a odd length cycle, then you can just generate different colorings and so on without doing anything that is well-informed or well-educated guesswork, just literally doing everything at random. Sometimes that works out quite nicely. Otherwise, for problems where you have to estimate some probability, if you don't know how to do it and the precision that's required isn't too big, then yeah, doing that kind of randomized solution is fine. Anything else?
Yeah, I think that looks like it's it for now for the live chat.
Okay, thank you very much for talking to us, Andrej.
Thank you for
I hope
having me.
everyone enjoyed the talk. I certainly did. See you all next time.
Bye.
Yeah. Thanks so much, Andrej.
Thank you, Andrej. Bye.